Hey everybody, hope everybody's doing well. So we're just going to kind of pick up where we left off. So we left off talking about the sun, which is a very typical star. This slide here shows the basic structure of the sun. So the outer region here, which is not typically visible to us on Earth, is called the corona. We do see it when we have um, solar eclipses happening, immediately followed by the chromosphere, and that gives us the part of the sun that produces its color. So it's what gives the sun its yellowish color. The photosphere is immediately beneath that, and that is the sphere where all of the light is being released from. And then you have the interior parts of the sun, and you've got two zones. You've got this zone right here, which shows it kind of looks like these black circles here. This is called the convection zone. That's when you get rising and sinking of solar material based on temperatures. And then underneath that, which you can't see, you have the radiative zone. This is where you've got a lot of that nuclear thermal force being pushed out from. And then, of course, you have the core in the middle of the sun. So quite a big difference in terms of temperature. You know, we're up about 5,800 Kelvin on the outside of the sun. The core is 15 million Kelvin. The other features also change, things like the density and whatnot. Now you can also see down here this little blue dot. That blue dot there is Earth relative to the size of the sun in terms of a comparison. And there's other surface features that we're going to talk about, solar prominences and some sunspots. We're going to talk about each one of those. On the next slide here, I have a picture of what the solar corona looks like. And so you can see if we black out the sun, you can see the presence of that solar corona. So in terms of its basic structure, the sun is not very dense. It's got a density of about 1.4 grams per cubic centimeter. Uh, its composition is about 95%, just shy of 95% hydrogen, 5.6% helium, and then there's some trace metals in there, about 0.1%. As I mentioned, surface temperature is just about 5,800 Kelvin, and the core temperature is about 15 million Kelvin. We know the composition of the sun because we can use the spectral analysis to actually look at what kind of spectral lines we're seeing and what elements they match up to. So anyways, next little bit here into a little bit more information. So the photosphere is the sphere of light. It is the visible surface of the sun. The chromosphere is the sphere of color, as I mentioned already. It is visible during solar eclipses. That chromosphere also produces that color. And then we have the corona, the solar corona, and that's the outermost atmosphere. The outflow of gas in this region is called the solar wind, which is protons and electrons that have escaped the sun's gravity, and that's just caused by the force being pushed outwards. There we go. So there's the structure of the inside of the sun. As I mentioned already, you have your core. Then, of course, you have your radiative zone, which radiates outwards. And then you have your convection zone. And then that convection zone causes things to float and sink to the surface of the sun based on temperature and temperature variances and density variances. In terms of the sun's interior, we have a thermonuclear core, so there is going to be some nuclear fusion going on. The central region of the sun where fusion takes place is what we call that thermonuclear core. And then immediately above that, we have our radiative zone. It's a region inside the star where energy is transported outwards by the movement of these photons. So we've got photons that are being produced. It takes many, many, many years for the photons to get through all of this zone here. And then, of course, we have the convective zone. As I mentioned already, it's the part where you get heat flow. So gases rise and sink depending on temperatures and densities. We talked a lot about the equilibrium in terms of stars and star size, and nothing is different with regards to the sun. There's a delicate balance of hydrostatic equilibrium from gravity pulling inwards and the pressure from the nuclear reactions pushing outwards. And so when you get into an equilibrium where the force pulling inwards and the force pushing outwards is the same, you get a star that holds relatively the same size as it continues to go through its life there. Now, of course, if any one of those forces changes, then the size of the actual star changes. So gravity, if it starts getting bigger, if the sun's maybe absorbed some material or whatever, and it's more massive, then you end up pulling in further, the sun gets smaller. If you've got more pressure from the inside, the sun's getting hotter, then it's going to push out furthermore, the sun's going to get bigger, etc. Or vice versa, right? Gravity can also get smaller if we're ejecting material out into space. The mass goes down. Gravity can't be as strong, and so the pressure pushes outwards. You can also get it to get bigger in that capacity there. So I already mentioned this, the hydrostatic equilibrium. So that's the outwards force. When it balances with the inwards force, you get the size of the sun. This is a nice little graphic here that kind of explains how the different parts of the sun may change. So on the left-hand side, we've got density, and on the right-hand side, we've got temperature. So you'll notice that the density at the outside is much, much, much lower than as you go into the center of the sun, right? So we've got the center of the sun, the core, you're at 150 grams per cubic centimeter density, whereas on the outside, you're much, much, much smaller, okay, in terms of its density. And so, and that has to do with, you know, the amount of gravity there, pushing things together, squeezing things together. They become more or less dense depending on where you are in the sun. The temperature also changes, right? So as the density changes, you increase density, you also increase temperature. So you can see on the outside, just about 6,000 Kelvin, 5,800 Kelvin, somewhere around there. And then as you go towards the middle, where it gets much more dense, there's a lot more material there. You get into the temperatures at 15 million Kelvin, which is really, really, really hot. I mean, it's not that hot in comparison to some other suns or stars, but certainly very hot in comparison to the outside surface of the star. And then what's going on inside the sun? So this is an example of the proton fusion reaction. This is where you get hydrogen atoms fusing together to form helium atoms. Now, I'm not going to expect that you guys are able to regurgitate exactly what is going on in terms of this, but this is a nice little graphic that helps us. So you got two hydrogen atoms here, two hydrogen atoms here. They will start fusing together, and when they fuse together, they spit out a neutrino and a positron, so that you can see that here. And then what ends up happening is you form this hydrogen version called deuterium. So you've got one proton, one neutron here, and then that will fuse with a second hydrogen, and then if you look on the other side, it's the same thing happening over and over again. You get another hydrogen coming in, and when this hydrogen comes in, it spits out a gamma ray, and you end up fusing this hydrogen with the deuterium. So the protium here will fuse with the deuterium, and you produce this helium that has a mass of 3. So it's not the typical helium, which has a mass of 4, but it's a helium which has a mass of 3. Now this is happening in parallel on the other side. And so now I have two helium atoms, each with a mass of 3, coming together. They spit out two other hydrogen atoms and fuse together to form the helium-4 that we are familiar with here on Earth. So here's your helium-4. The word helium comes from the Greek word helios, which means the sun. And so you get two protons, two neutrons, as being spit out, and that's accounting for the 5 or so percent of the mass of the sun being helium. Of course, before reaching the atmosphere, photons are generated inside the core. So photons are packets of light, and they travel through the main body of the sun called the interior. And they actually go through a zigzag path on their way out. It takes a long, long, long period of time for these photons to actually get out to the surface of the sun. So many interactions occur that it literally takes hundreds or even thousands of years, as I mentioned, for these photons to get from the center of the sun to its surface. Of course, you know, hundreds of thousands of years, hundreds or thousands of years to get to the surface of the sun, and then of course that particular photon would leave the surface of the sun, and then it only takes about 8.3 minutes to get to the outside of the Earth, right? So it moves a lot faster once it gets out into space. Another effect of what you get with regards to this is optical depth or limb darkening, and so you can see here We also have surface features that are very interesting. These are called sunspots. If you take a look here, Earth, very small in comparison. Now, sunspots are really, really, really interesting. They are caused by magnetic disturbances on the surface of the sun. This is a close-up picture of one. Now, I understand it looks black and whatnot. It's still extremely hot. They are cool areas of the sun's surface. They're cool, but cool relative to how hot a sun would be. You also get these other features on here. Look, they're called granules. You get this granulation over here. This thing is absolutely massive. So 23,000 kilometers across. Our Earth is much, much, much smaller than one of these sunspots would be. Now, in terms of what causes these, and we're going to get through that right now. So granules, these are convection features that are thousands of kilometers in diameter, and they are seen constantly on the surface of the sun. Sunspots are, as I mentioned already, are temporarily cool regions of the sun, and they're produced on the photosphere, and it's caused by protruding magnetic fields. And there's a diagram that I'll show you a little bit after that'll help out with that. And then the last part, a close-up of these sunspots shows that they do have a darker inner region, which is what we call the umbra. And then surrounding that region, we have a lighter region called the penumbra. Now, here's an interesting graph here. This graph looks at the number of sunspots that we can see on the surface of the sun relative to the year. And what you'll see is it looks like it goes in cycles. In fact, it does occur where you have solar maximums and solar minimums in 11-year cycles. So right now we are getting close to a solar minimum. So this would have gone up over 11 years, probably reached its peak around 2010, and now we've gone down and we are reaching our solar minimum right now. In terms of how these sunspots come to be, you end up getting the sun rotating at different rates depending on where it is, where the location of these sunspots are. And as these things rotate at different rates, you get the magnetic field, which is now coiling. It develops these kinks. So as you can see, it kinks outwards. And where it kinks outwards, you produce surges or changes in magnetic field around the sun. And so you end up getting a protrusion in two spots, one where it exits and one where it enters the sun, and you produce these sunspots. In terms of solar cycle, the rotation varies. So once every 25 to 30 days, the sun will go around, spin around itself once. This differential rotational twist, as I mentioned, because if you have some regions that are 25, some regions that are 30-day, this differential rotational twist is what causes these sunspots to appear and then disappear at different times in 11-year periods. There's a beautiful diagram called Maunder's butterfly diagram, which I do have set up on the next slide here, and it actually will plot the latitude of each sunspot as a function of time. So here's what you're looking at here. So here's your dates, so all the way up to the year 2000, and here is the sun's equator, 30 degrees north, 90 degrees north, 30 degrees south, 90 degrees south, north and south equator of the sun. And then what it does is it plots out the location of the sunspot. So each one of these little dots that you might have here, these red and yellow dots here, represents a region of space or an amount of space that is taken up by these sunspots. And so you see, as you move more towards the poles of the star, you don't get as many sunspots, much more prevalent at the equator. And that's just from the differential equation, the spinning of the sun being different at different areas. And so you get these kinks in the magnetic field, and then ultimately what you produce is this diagram here, this graph. It's called Maunder's butterfly diagram. So why are sunspots so dark? The reason is because right underneath the surface you have the convective zone where you got hot rising gases, and then the cool ones tend to sink. But because of this magnetic field presence there, it actually stops that hot rising gas from coming up. And so if there's no hot rising gas coming up, the surface where that magnetic field comes out will will be cool, or cooler, I should say. And so you end up with a situation where you get these cool spots on the surface, cooler spots. One of the other features that we see with this is called the Zeeman effect. And so we can actually map out these spectral lines on a star like our sun. And so what we end up seeing is we get regions where you get this thing called the Zeeman effect. And what the Zeeman effect is it's a splitting of the spectral lines of hydrogen gas into two or more components. And so when there is no magnetic field present, you end up getting a single spectral line. But when you turn the magnetic field on, or when the magnetic field is present, it actually takes that single spectral line and splits it into multiple spectral lines. And so that's a good way of telling whether something is going to be, or whether there's a sunspot present or not. We look at the spectral lines and whether they've split or not. Solar prominences. So these are enormous ejections of material from a star. Of course, they come out of the regions where there are sunspots, and it's basically the magnetic field just pulling material off of the sun itself. So the first one, of course, is a diagram. The second one is an actual picture of the surface. And I do have some more pictures here. So interesting in terms of the size. These things are absolutely massive ejections here. There's the Earth in terms of its relative size to one of these solar prominences, just for a comparison. So as I mentioned already, these are flame-like protrusions. They are seen near the limb of the sun and extending out into the solar corona. These are mass ejections. They go out. And then, of course, auroras, which are can be caused by an interaction with this solar wind, are present when you have mass ejections from the sun, a lot of them. So we do oftentimes, we will look at what's going on at the sun, see whether we'll be getting more or less interaction by our atmosphere with these auroras and whatnot. And then, of course, in terms of what makes the sun shine, we know that 4 hydrogen atoms goes in terms of the thermonuclear fusion reaction that we saw up top. And as a result of fusion, we get 1 helium atom and plus a lot of energy. And when we look at the most famous equation of all, E equals mc squared, it actually tells us. So we can convert matter directly into energy. And so you don't need a lot of matter, because this c value, which is the speed of light, if you square that value, we're talking about something in the order of 9 times 10 to the 16 in terms of its magnitude. And so you don't need a lot of matter to produce a lot of energy. And so the sun is going through this right now. It's producing tons and tons and tons of energy by converting some matter directly into that energy there. If you guys have any questions, please email me. There is a reading on the website that you can do. And I'll see you guys for tomorrow's lessons. See you later.